Welcome to the deep dive. Today, we're digging into some sources that propose a really different way to think about gravity. Forget space-time curvature for a moment.
Yeah, it's quite a shift. We're exploring this thing called the phase kernel model. The core mission really is to ask, can we describe gravity purely as like an effective refractive index for signals?
Instead of general relativity's geometry.
Exactly. Can this different language, this wave-based view, perfectly reproduce Einstein's results, at least where gravity is relatively weak?
Okay, so let's unpack the main mechanism here. It hinges on something called the phase kernel.
Right.
Let's maybe set aside the exact notation for a minute. Fundamentally, it's measuring how much phase delay a signal picks up per unit of distance it travels, correct?
That's the idea. You add up all those tiny delays along the path, and that sum is the gravitational effect.
So instead of space and time warping, we're talking about, well, the local speed of light changing slightly.
Pretty much. We define an effective refractive index, let's call it num, that's usually just 1 in MP base, but near a mass, it becomes slightly different from 1.
And that difference depends on the gravitational potential.
Directly proportional to the Newtonian potential, phi. Since phi is negative, this net of all actually becomes slightly greater than 1.
Ah, okay. Greater than 1 means the signal slows down, which means a delay.
Precisely. And that brings us straight to comparing it with general relativity. Think about the Shapiro delay.
Right, the classic test. Light taking longer to travel past the sun, for instance. GR explains that as light moving through time that's stretched by the sun's gravity.
Well, this phase model gets the exact same delay. It has to, based on that refractive index being just over 1 near the mass.
So you calculate the delay just by integrating, by summing up those tiny phase delays along the light's path.
You got it. And here's the kicker. The total time delay you calculate this way, delta TECMA, turns out to be numerically identical to the standard weak field GR Shapiro delay, delta TGR.
Wow, okay. Same number, different reason. GR says space-time curvature. ECM says it's an effective slowdown represented as a phase shift.
It translates the GR time delay directly into phase units. The algebra forces it if you define the kernel based on the potential.
Okay, that works for time delays. But what about something like gravitational lensing, where light bends? Isn't that inherently geometric? Doesn't the path itself change?
That's a really good point. Lensing delay does have two pieces, right? There's the extra path length because the route is bent, the geometric bit. And then there's the Shapiro delay along that path because the signal is slowing down.
So does the phase approach capture both?
It does. When you work through the phase calculations, it naturally reproduces Fermat's principle for light paths. The potential term lines up perfectly with the Shapiro integral we just talked about, and the other term correctly accounts for the extra geometric path length. It all falls out.
Okay, impressive for light. But gravity affects matter too. How does this phase idea handle, say, planetary orbits? Mercury's perihelion precession is the classic example of space-time curvature in action.
Right, that's usually seen as Mercury following a geodesic, a straight line through curved space-time, which looks like a precessing ellipse to us.
So how does the phase language deal with that? There's no light signal here.
We translate it. Instead of a curved path, we think of it as the orbit accumulating a tiny extra bit of angular phase on each revolution. Like the orbit itself is rotating slightly forward each time.
An extra angle increment. Delta chi you'd call it. So not the coordinates bending, but the object gaining a little extra angular momentum effectively over time.
Sort of, yeah. It's like a cumulative angular shift. And what's really striking is when you do the math to figure out how much that extra angle is per orbit, you get exactly the same formula as the standard GR calculation, the famous frac phi GMA 1E2C.
So the prediction is identical. Again, it's the interpretation that's different. Phase accumulation versus moving in curved geometry.
Precisely. It's a different conceptual framework, a different bookkeeping language, as some of the sources put it.
Which leads to how you might actually test this.
Yeah.
If this phase kernel approach is just a rewrite of GR, how do you test it? Or test deviations from GR using it?
That's where it gets interesting for experimentalists. You can define parameterized phase kernels. Start with the basic one derived from Newtonian potential. Let's call that model A, which matches GR.
Okay.
Then create a model B, say, where you add small correction terms to that kernel. Maybe terms that depend differently on distance, like phi 1 plus A1 fras, where $1 is some parameter you want to measure.
Ah, so you're parameterizing potential deviations from the standard GR Newtonian form, but within this phase language.
Exactly. Then you take your best data sets and fit for those parameters, those Adel coefficients.
What kind of data provides the tightest constraints?
You need the highest precision stuff we have. Solar system Shapiro delay measurements. Cassini data is crucial here. Viking too. Then there's very long baseline interferometry VLBI, looking at how quasar positions shift when they pass near the sun. That measures deflection.
And pulsars.
Absolutely critical binary pulsar timing, especially systems like Hulse-Taylor. You look at the arrival times of pulses over years. The residuals, the tiny deviations from a simple model, are incredibly sensitive to gravitational effects.
And the goal is, see if those fitted parameters, like $1, are consistent with 0.
That's the test. If all the A parameters are 0 within the measurement errors, then it confirms that standard GR model A is sufficient in this phase language. If any Ehlers is consistently non-zero, well, that would be big news, suggesting a modification to gravity.
So wrapping this up, the real power here seems to be that this phase kernel model acts like a perfect mirror to general relativity, at least in the weak field limit where we do most tests.
It provides an alternative mathematical structure, yes, one that reproduces the numbers without explicitly using a space-time metric.
Which leaves us with a pretty deep question, doesn't it? When you think about how we actually measure these effects, timing pulsar signals using interferometers, these are fundamentally phase and time measurements.
They are. We measure phase differences, arrival times.
So the provocative thought for you, the listener, is this. Is the underlying geometric picture of curved spacetime the fundamental reality? Or, given that our observations are often directly phase-based, should we perhaps consider a physics where phase itself is more fundamental? Is gravity ultimately about spacetime geometry? Or is it about phase shifts in quantum fields? Something to mull over.